see if it works.
You got rid of the computer from 1936.
Well, it was like 3 years old. It wasn't super old, but it was slow and tiny screen. This one's actually pretty nice. All right, guys. So let me get out of here. Hey, turn with me to that. I heard you. Hold on.
Yeah.
All right, guys. So we're starting a new section.
We get assignment sheet?
Yes. Assignment
You're like, I'm gonna pass it out.
sheet. All right, so if you are ADD like me, I don't know what to tell you, but really try to focus. There's a lot of good stuff in here. It is all over the AP test. And in my opinion, it's some of the easiest stuff to do on the AP test once you know how to do it. Okay? There's some formulas involved in this that you do not have to memorize if you're just thinking. And if you really think, it's going to make a lot of sense. Now, is anybody in here in Physics C? Just one? Man, I used to ask that question, and it would be 2/3 of the class. Hopefully those numbers will get back as people start getting to know Health and liking him and know that he's a good guy. So, in Physics C, you have already learned how to integrate, I'm guessing, right? And you've probably done integrals with the little numbers at the top and the bottom, right? So if he's the only one, I need you to pretend you don't know that anymore, okay? For now. It's great that you know that, but we have learned how to integrate. What we have not talked about is what we're actually doing with an integral, okay? Now, what you might know is that an integral is kind of getting you back, right? If you start out with a function, you take a derivative, you get a dy dx or dy dt. When you integrate, you get back to that original y, okay? But what is it doing when I start you off with a function and you're integrating? Well, if I start you off with a function and you're integrating, we might call that the antiderivative because you're going back. You're basically erasing the derivative that was done if there was a derivative done. But mathematically what you're doing is finding the area between that curve and the x-axis. All right? Now that will mean something in the context of the function. Like if the function is velocity, when you integrate, it basically takes you back to position. So if I integrate a velocity curve, I'm finding the area under that. That's how far I went. Or maybe my displacement, depending on what the function was. If I'm accelerating, right, I can find, and I integrate an acceleration equation, I'm kind of going back to velocity. But if I integrate a particular one, it's giving me the change in velocity. All right, basically, like maybe I went from 20 meters per second to 80 meters per second. Okay, so what we need to learn is before we actually start using our integral formulas, hold on to those for now. We're going to actually learn kind of the foundation, where calculus came from. And calculus came from somebody finding an area under the curve. And Newton took that and really went to the next level, pulling in limits and things like that. And then somebody, fortunately, came up with some integral rules that kept us from having to do this the hard way. So we're going to go way back to just the foundation of what's going on with finding area under the curve. And we're going to pretend we don't even know calculus for a second, and we're going to use some geometry. Okay, so for instance, I got a curve right here. This happens to be something like, I don't know, x squared plus 1 or something, and I've only shown it from 0 to 4. So if I were to give you something like this and say, what is the area under the curve, what would be your thinking if you were desperate, right? I've numbered these. Now notice I'm going by ones, right? So don't look at one box and go, oh, that stands for 1. It might, and it does in this case, but not because it's 1, 1, because it's what? This length is a half, and this height is 2. So it happens to be 1, but only because of the way I numbered it, right? So you'd have to go length times width. But if you were finding area, what would you probably do? Count the boxes. So first you might do something like, all right, well, dang it. First you might do something like, all right, well, let me count the whole. I know that's what, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So it looks like easily I have 18, right? And then you might just start doing stuff like, well, this, if I took that little part right there and filled that in, that would make a whole nother box, wouldn't it? So maybe these two things give me another one. And then maybe you go, all right, no, sorry. Maybe this and this, right? So I've taken care of both of those. And then you might say something like, well, if I took this little part and shoved it in there, then these two things would give me another one, right? And you could keep doing this, right? You could say, well, maybe, I don't know, I'm getting a little desperate here. Maybe this right here, this half, along with that half gives me maybe another one. And then maybe you'd say this little part right here, maybe fills in that part right here. It's not exact, right? But maybe that gives me another one. And then what am I left with? At this point, I have this and this little part. Maybe this little part fills in that little part and gives me another one. And then that little part right there maybe fills in, call it, maybe this little part right here and gives me another one. And what do I have left at this point?
The little part.
This and this. And that looks like maybe a little bit more than one, maybe a 1.1. So 18, 19, 20, 21, 22, 23, 24, 25.1 maybe. But I think we can all be honest and say that that's probably not very exact, is it? Now, it turns out that the exact value of this using calculus, which we're not even going to use right this second, but the exact value is 25 1/3. So we're actually pretty close just to eyeballing it. But what if we really wanted to be perfect? Now there is this process, okay? The process that we're going to be using is called Riemann sums, and it's spelled up there at the top, Riemann. In German language, they put the letter on the second letter. Like, when you see team, we put it on the first, right? But they use the second one. That's why stuff like Fleischmann's margarine. I don't know if you ever noticed Fleischmann's. They use the I, Fleisch. Well, anyway, it's called a Riemann sum, but people butcher the crap out of that because not everybody's lived in Germany for 3 years like I did as a young boy, and they might not know the language. So some people say Riemann, whatever, but it should be a Riemann sum. Okay, now there's all kinds of Riemann sums, but this is what Riemann started doing. He could have used tiny squares like we did. It's kind of painful, especially if our function is massive, right? What if we had 2,000 squares or 1,500 or 80,000? We don't want to count all those. So what he said is, you know what you could do? What you could do is take something and basically just divide the base up. So he said, let's just say we're trying to go from 0 to 4, and we're trying to find that area under here, right? What if I divided the base into equal parts? And by the way, that it's not always equal. I'm doing that today, but they're not always equal. AP realized kids got wise with their calculators and the programs, and there are a bunch of little things you can download for Riemann sums when the bases are different. When the bases are the same, and it makes it really easy to do it. And AP got wise to that and started making their bases different all the time, or a lot of the time. So they mix that up. So don't use any apps. I think it's a crippling effect. Or if they do, they'll just make it a non-calculated question. You won't have your calculator help you anyway. So they're wise to you. If you try to outsmart them, you're probably not going to. But what Riemann noticed was, what if I know the function, if I take the whole base, and the base is basically the ending point, the 4, and the beginning point, the 0, subtracted, and I divide it up into a bunch of parts. The first one we're going to do is just two rectangles. So we divide it by 2, and he said my base ends up being 2 units long. Then all I would have to do to find the area, and I know when you first see this, you're going to go, this is stupid. The area would just be the base times the height of the rectangle that he was shoving in there. Now the problem, and there's 2 kinds of rectangles, by the way. There are what we call right-handed rectangles, which means you take your base and you bring the right side up until I hit the function. And that gives me base is 2. And what would the height be? Now I know you can look at it and see that it's 5, but what Riemann did was basically say, well, I am going to plug in 2 into the function to get the height. That kind of makes sense, doesn't it? And that way, no matter how ugly my function is, I could just go, well, I know if I'm at 2, I plug it in, it gives me the height, and then I can go base times height. And that's what he's doing right here. The base, which was 2, and f of 2, which was 5, and I have the area of my first rectangle, which you can see does what? Gives me way more area than I need, don't I? But that's, sometimes Riemann will ask you to do that. And you'll get an area you know good and well is an overestimate. So what? You're doing what you're told. Now for the next base, I'm not starting at 2. I'm starting where? 2 over from 2, which is now 4, but I still have the same base. So I'm still going base and height. So I can still use 2 for my base, which is 2. But my height now, I would have to plug 4 in to find the height, and it ends up being 17. And again, I'm assuming I know my function. So now I have that base and that height. And that gives me this, because again, right rectangle, use the right side. And that gives me, again, a huge over approximation. So Riemann would have said a 2 rectangle right hand approximation for this area would be 44. And you know that that's clearly too much, isn't it? Well, that's because I only picked 2 rectangles. What if I went with 4 rectangles? Now, 4 rectangles, you can see, is clearly less of an over approximation, right? Because look, this was the first one we had, right? And it had all this extra space I'm not going to include. You all with me? But I still do have extra space that I am including. All of that, all of that, all of that, all of that. So you can still see I'm going to be over approximating, but walking you through the process again, here we go. So if I knew that I was going to integrate from 0 to 4, then my base ends up being what? My base, I take the furthest I'm going, I subtract where I start, and I divide it by the number of rectangles. So very clearly, I can see that each base would have a length of 1. Now again, they're not always the same. Sometimes I tell you the bases, and you use those if I tell you. All right, and then I need to know the height of each one. Well, if I start at 0, and I don't always start at 0, I would go over 1. So if my base is 1, how do I find my height? I find f of 1, right? So I plug 1 in my function and I get that height. And then here is my base times height. So that first rectangle has an area of 2. Then I say, all right, my next base is also 1. But to find my height, I got to go over again 1. So now I'm plugging what in? F of 2 for my height, right? So base times height, 1 times 5. And then my next base is also 1. But how do I find that height? I plug in the right side, 3 into my function, whatever it is. In this case, it ended up being 10. So there's another area. And then next base is 1. But what's the right side of it? It's at 4. Plug 4 in, I get 17. And I add it up. And what did you notice going from 2 to 4 rectangles? I'm a little closer to the real thing, aren't I? Because I have less of an overestimate. Now, what happens if I go to 8? I'm not going to walk you through the same process again because we have some practice problems. But what do you notice? Less overage. Let me ask you a question. What do you think happens the more rectangles I get? The skinnier they are, right? And the skinnier they are, what do you notice about the overestimate? It decreases. Well, what if instead of having 4 rectangles or 8 rectangles or 16 or 100, What if I went to an infinite number of rectangles? What's happening to my base the more rectangles I get? It's getting smaller. What's that approaching?
0.
What does that sound like?
Limit.
A limit? I've got a limit problem. Now I still have to sum them. So I'm basically limiting a sum. I can literally put an infinite number of triangles in there, and it basically ends up being these little infinitely small bases times heights. What do you think they almost look like? An infinitely small base times a height. Almost like a line, right? It's almost like I'm putting little lines in there. Little lines are going to have very little overlap, are they? And I'm going to be able to find the exact value of this. That's where we're heading. But with a Riemann sum, we are going to be doing, you're going to have over, under, you're going to have error in there. Live with it. In fact, please, sometimes the mistake people make is they get the function and they see the integral and they go, oh, I can integrate that. And they use their integral rules and they find the exact answer. But the question is, use a right-handed Riemann sum with 4 integrals to approximate the answer. And you write the right answer down. Of course, it's an option on a multiple choice question and you miss it. You miss it for being better because you didn't read the directions. So when it says Riemann sum, you have to do what you're told on that, not just be exact. It's very important. Are you with me? But essentially what we're doing is finding an integral. Like this whole process, if I was really on my game, you know what I'm saying? I'm saying the integral of this function, dx, from 0 to 4 is about 29.5. I am literally integrating the function, except I'm not using integral rules. I'm using Riemann's approximation. And it is a huge deal for AP Cal. And if you know this, to me, it's just taking candy from a baby. Now, you'll notice I used what we call right rectangles, which means I'm going to split up the bases and I'm going to bring it up until the right side hits the curve. There's also left rectangles. There are also trapezoids, and then trapezoids are, in my opinion, probably the best, but there's also midpoint approximations. So midpoint, and all these I'm talking about look like this. So here's a curve. I'm trying to approximate that area. There are 4 different ones that we have to know for our AP test. And I think these are the only ones you came up with, actually. There are right rectangles, left rectangles, and if it says right or left, that means bring up the rectangle to the right side. If it's left, left side hits the curve. So you use that side to find the height. Midpoint rectangles and trapezoids. So let me run through quickly how you'd actually do each one. I'm not going to do right since we just did one like that. But there's the picture, and you can see I'm bringing up the right side. Now, how about this? Now when I'm doing right, just like I did before, what am I going to end up when I find my area here? An over approximation? Under approximation. So this is actually a huge question on the AP test. Happens every year. So when do you know right hand over approximates? And when do you know right hand under approximates? So what do we call when the curve is coming down? We said when the curve is decreasing, then what will a right do? Decreasing, it under approximates, doesn't it? But you saw before, when it's increasing, it over approximates. Well, what would a left one do? Increasing. Under. And what would a left one do when it's decreasing? Over. So on the increasing, a left will under. And if you need to sketch a picture, sketch a picture. Okay? But don't sketch a picture for an answer. Just make that statement. Like, so if they ever say, hey, is this an under approximation or an over approximation? And you know it's decreasing, you could go like say I was going from 4 to 10. You could go, oh, left-handed Riemann sums always overestimate decreasing functions. Just like left-handed Riemann sums always underestimate increasing functions. Now, if it does both, you're probably getting a better approximation, right? Because you got a little under, a little over, probably meets closer to the actual value. Here's left. You notice it? I'm going from 2 to 10. And notice I'm bringing up the rectangle till the left side hits. So how do I find the base here? How do I find the area here? I take the base and I multiply it by what? Whatever f of 2 is, because I'm doing a left hand one. If I was doing a right hand one, I'd use f of 4. What do I do here to find the area? I take the base and multiply by what? F of 4. If I was doing a right-handed rectangle, I would take the base and use f of 6. Are y'all seeing this?
This seems like an outdated. So like, why is it so important to A, B, then?
You'll have to ask me. Surely don't know. Now, if you don't have a function, what if I don't have a function?
Then you got-
Like, what if I just have a picture and I don't have a function? I had to sod the back of my house. I had a terrible septic issue, got it fixed, had to put all new sod in. How do I know how many pallets of sod? Pallet of zoysia right now costs $330. Roughly, might be more than that, just for a pallet. I looked at my backyard and I'm like, how do I know to order? If I over order, like what if I have an extra pallet of sod? What are you gonna do with an extra pallet of sod? Throw it away? Where do you even throw it away? It weighs a ton, more than a ton. You're gonna put it in your dumpster and try to wheel it to the curb? Things gonna fall apart when so you're stuck with this sod. So what did I do? I mapped out a little diagram of I took a picture of my I actually have a decent picture from overhead, picture of my sod, and I did a Riemann approximation on it to find the area. I did. I took a bunch of bases. I know my wife's like, you're such a nerd. I kid you not, left over enough sod to do like maybe a 3x5 piece. That's it. So you consider, I basically, and that's what you probably want to do is you want to have a little extra. You don't want to not have any and go, crap, I don't have any sod. I got a hunk of dirt right here left. So you always want to be a little bit over on materials. It was awesome. The bell rings when? 2 minutes. Okay, try to stay with me. You're probably not going to be able to do much on the homework side. Do the best you can. We'll try to catch up. Last two, though, midpoint. Midpoints are great because midpoints, stay with me, say to do this. Once you figure out, stay with me because there's kind of a difference here. Once you figure out your base, you're not going to use the left or the right. You're going to use the middle. Well, if left uses f of 2 and right uses f of 4, how do you find the one in the middle? You average them. So you average the x's. What's the average of 2 and 4? 2 plus 4 is 6 divided by 2 is 3. And you plug in f of 3 to find that height. What's the average of 4 and 6? 5. You plug in f of 5 to find that height. So you're using these middle heights. Are you with me? So, and then you use the bases. Trapezoid. I like trapezoids a lot too. Trapezoids, instead of, now the one thing about midpoints is great. You got a little over, a little under, a little over, little under, a little over. Almost on all of them, it kind of balances out. These, you can see there's very little over, but dang it. Hey, we'll catch up tomorrow. There is a homework assignment. We probably aren't going to have much luck with it. No worries. We'll figure it out.
Sir, if you don't need another math class for a major, you still take another math class?
Of course. And I'll go one step further.